Hello everyone. Today we're going to be doing the second part of min and max problems. This one is a little bit, it's still related to maxes and mins, but we're dealing with boundaries now. So let me grab my pen. So you might remember from Calc 1, if we had an interval, okay, say from here at x equals a until x equals b, and we were interested in everything that's like in here, right? And you asked like, oh, what's like the absolute maximum or the absolute minimum in this region? So what you would do is you would have this function f of x, you take its derivative, set it equal to 0, and solve for x values, and then those x values are going to be critical points, okay? So you're going to have one critical value right here, call that C1, and then you're going to have another one right there, call that C2, right? But in this kind of scenario, you should also check, you also have to check for endpoints. So honestly, let me just redraw this. Let's say the curve looked like that. Yeah. So you're going to have to check your endpoints too. So you're going to take what f of a is, what f of b is, right? These are your endpoints, a and b. And then you're going to do f of c1 and f of c2. And your absolute maximum is going to be, if we look at the graph back here, it's at point A, at x equals a, that's our highest point. Our lowest, maybe I didn't draw this too well, but we'll just say C2, f of C2 and f of B are about equal. So that'll be your lowest point, okay? That'll be our absolute minimum. So yeah, we're doing the same thing, except where we're going to have these like kinds of limits that we have to check, the limits being x equals a and x equals b, but we're going to do it with multiple variables. So what that's going to look like is you're going to have they're going to give you a surface. So something like that. And then they're going to give you a region, say like a square, for example. And they're going to say, oh, in this region, what are like the absolute maximum and minimum values? So yeah, maybe this is going to be well, honestly, this could be an example we're going to do soon. Let's just do this. Okay. This, for instance. Right, so if we're observing this paraboloid right here, and our boundary is this circle, and we wanted our absolute minimum points and our maximum points in this boundary, in the boundary of the circle, how are we going to find those? That's what that looks like. So yeah, so you could kind of tell, if you keep going up, you're going to have this, they're going to intersect in this sort of ellipse, and your absolute maximum point would be right at that little tip. That's what she said. And your minimum point is going to be this, the traditional critical point of the paraboloid. But that's not always going to happen. Depends where they intersect, right? But that's kind of what I'm trying to get at here. So let's do like something really simple, not quite something with a circle. We'll do that later, but we'll start off really simple, and we're going to take it super slow. So say they give us a paraboloid. They tell us z equals x squared plus y squared minus 2x minus 4y plus 10. So this is pretty evidently a paraboloid because you can complete the square with these two x terms and with these two y terms, and you'll see that it's just an off-centered paraboloid. It's actually the same paraboloid I showed earlier in Desmos. Okay, yeah, and then so that's our surface. This is the surface. And what does our boundary look like? Our boundary is that it has to be inside a triangle. So inside a triangle with these three vertices. With vertices of, let's see, 0, 0, 4, 0, and 0, 4. Okay. So what's the best way to kind of look at this is okay. Well, the very first step is find your critical points. Actually, while we're at it, we could also draw our boundary. So you have 0, 0, that's the origin, and then you have 4, 0, that's like somewhere out here, and you have 0, 4, it's like somewhere up there. So here's the triangle we described, and you could use basic algebra to find what these are. So this right here is just x equals 0, and then this guy right here is y equals 0, and then this line right there, he goes from 4, 0 to 0, 4. That's going to be y equals 4 minus x. Right? So our boundary is defined by these, what do you call it? These lines and stuff. Okay, so now let's find our critical point. So this is our surface. So to find our critical point, we just take the partial with respect to x and the partial with respect to y. And we set that equal to 0. So partial z partial x equals 0 equals 2x minus 2. And then partial z partial y equals 0 equals 2y minus 4. Okay? So then x equals 1, and then y equals 2. So that our point is 1, 2. That's our critical point, okay? Now, we have to also observe whether this point is inside of this region. If it's not, then we don't care about it. So let's see, 1, 2, that's most definitely in this region, right? That's before 4, so it's like halfway to 4. But, oh, that's 2, my bad. It's like somewhere here, if this is 4, and then it's about here. So that's in our region, right? So we can keep this point. This is going to be in one of the points we're going to have to plug in at the very end to find if it's a min or a max in this boundary. Okay, now let's go through our different what do you call it? Boundaries, right? We have y equals 0, x equals 0, and y equals 4 minus x. So let's start with y equals 0. So what you could do is you could really just plug y equals 0 into this equation right here, and you're going to get, well, maybe I shouldn't write z, but the better way, in my opinion, to think about it is that if you plug in y equals 0, you're only going to have a function of x in this scenario, right? You're going to have that. And this function of x has a minimum and it has a maximum, or well, it's going to have one or the other, either a min or a max value. We'll have to plug it in at the end to find out what that's going to be. So you could find this critical point, obviously, by just taking the derivative. So you're going to get 0 equals 2x minus 2. now x is going to equal 1. So we have another value at the border when y is 0. That's going to be this. Okay? So this is another point we're going to have to plug in at the end and see how, if it's a min or a max. Okay, now what about x equals 0? Similar thing, except now you have a function of y, right? Because all the x's go away. And you're going to have y squared minus 4y, plus 10. It doesn't matter, it's going to go away with the derivative. Okay, and you're going to get 0 equals 2y minus 4. So then y is equal to 2. So then your other point is 0, 2. This is another point we're going to have to plug in at the end and see how high it is. Okay, now last point, or last thing, y equals 4 minus x. So same deal. You're going to get a function of x now. And yeah, so now it's just going to be a function of x equals x squared plus 4 minus x squared minus 2x minus 4 times 4 minus x plus 10. Okay, so now we could take the derivative. 0 equals x squared plus 2 times 4 minus x times -1 minus 2 plus 4 times 4 minus x. That's just a, oh wait, did I do that right? No, I did not. This is a constant, 16 minus 4x. Oops, I think I did this wrong, I'm being silly. This is minus 16 plus 4x. So yeah, that's just gonna be plus 4x, or plus 4. Okay, hold on, I'm being really stupid right now. So you have x squared, and then you distribute this out, you're gonna have plus 16 minus 4x, so minus 8x, plus x squared, minus, is that 2x, minus 16, plus x squared, plus 10, and now you take the derivative. 0 equals 2x minus 8 plus 2x minus 2 plus 2x. And yeah, now you you combine. Wait, where did I get this x squared from? Oh, I'm being really stupid. I'm off my game right now. So this is plus 4. I'm sorry. Okay, so now if you combine these, you're gonna have 4x, and this is minus 10 plus 4, that's minus 6, equals 0. And then if we solve for x, we're gonna get x equals 6 over 4, which is 3 over 2. Okay, and now we also know that in this case, y is equal to 4 minus x. So 4 minus 3 over 2, that's just 8 over 2 minus 3 over 2, and that's 5 over 2, right? So our final point that's like important to us is going to be 3 over 2, comma 5 over 2. And we're going to plug in all of these points back into the original function to tell us how high up they are, what z value they give us. So let's see. So let me rewrite those down. We had 1 2 1 2 1 0 0 2 1 0 0 2, and then 3 halves, and what was it, 5 halves? 5 halves, yep. Okay, and then our paraboloid was z equals x squared plus y squared minus 2x minus 4y plus 10, wasn't it? X squared plus y squared minus 2x minus 4y plus 10. Yep, sick. Okay, so let's do f of 1 comma 2. This is going to be 1 plus 4 minus 2 minus 8 plus 10. All of these guys cancel. You get 5. Okay. F of 1, 0. So all of the y terms go to 0. You're going to have 1 minus 2 plus 10. And that's minus 1 plus 10. That's just 9. And then let's do f of 0 comma 2. The x's go away, but now you have 4 minus 8 plus 10. That's 6. And then f of 3 halves and 5 halves. It's going to be 9 over 4 plus 25 over 4 minus 6 over 2 minus 20 over 2 plus 10. Okay, so let's simplify this a little bit. So 9 plus 25, that's 34 over 4. These guys are going to be minus 26 over 2, but that's minus 52 over 4. And then that's 40 over 4. So let's see, that's 74 over 4 minus 52 over 4, which is, what's that, 22 over 4. Okay, which is just 11 over 2. Okay. So we could see that this is our max, this is our highest point. And then this is what is this, 5.5. Okay, so this is our min. Okay. So let's see how that fares up with our Desmos plot. So we had these points, 0, 0, 4, 0, and then 0, 4. So we had y equals 0, x equals 0, y equals 4 minus x. And then, oh yeah, and then we could also choose the points we have. Right, so we also have 1, 0, 9. And then 0, 2, 6. And then 1.5, 2.5, and 5.5. Okay. So this is kind of messy, but we'll try and take it very organized. So first is going to be our critical point, which we learned how to find earlier. So you could see that's just the little blue dot right there. This is our boundary. Okay, so that's pretty standard. We know how to find that. Now, if we look back here, for y equals 0, we have this point, which is 1, 0. And for that, we got a height of 9. So our point is 1, 0, 9. So let's see. So that's going to be on y equals 0. Yeah. So there's that. You can kind of think of it like you have this cross section of y equals 0, and it creates this parabolic shape, and you're just finding where that critical point is for that parabola. So that's where that comes from. Now, next part, we had 0, 2. at x equals 0. So same kind of deal here. This is 0, 2, 6 at x equals 0. And if we want, we could compare it to the previous point right there. Right, so there are those 2 points. Obviously, we found that this guy was the highest, 0, 2, 9. Or no, sorry, this guy. This guy was the highest, 0, 2, 9 on when y equals 0. Okay, and now our final point is on that line of y equals 4 minus x. And he's hitting there at, he's hitting our graph at 1.5, 2.5, 5.5. So let me change the color of this plane because for some reason, okay. So there he is on that diagonal line. Okay. So yeah, I guess with this one, it really helps to think about it like you have these planes and they're cutting your paraboloid into cross sections. And as we know, okay, that's a really ugly paraboloid. As we know, the cross sections of a paraboloid are parabolas, right? So whenever you get these parabolas, you can, when you get these parabolas, you just take a derivative and you could see where their minimum or maximum value lies. And then you compare all of the points at the end. So yeah. Okay. Now we could move on to a harder example of this. Well, actually, yeah, I think in my notes, oh, I guess I changed the curve. Anyhow, we'll see what happens when we have an elliptical boundary. So here, so you have x squared plus y squared minus 6x plus 9. This is our new function. Okay. And now our boundary is an ellipse. This ellipse has this equation, 3, okay, well we'll just label these for clarity. And then our boundary is 3x squared plus 9y squared equals 1. Now, I guess my general rule of thumb is they either give you straight lines or curved lines. And the curved lines always have to, any kind of boundary they give you has to be closed. Meaning, they cannot give you a boundary. So say we'll use the same surface. We have a paraboloid again. Excuse my god-awful paraboloids. But yeah, say we have a paraboloid again, and then they tell you the boundary is another parabola down here. That doesn't make any sense because the parabola, it doesn't have a closed area. It could go all the way out here, and this means there's no. This means the absolute maximum is infinity, because this means this guy is unbounded. He could keep growing and go on forever, and there's no like finite number to describe that that maximum. So that means this parabola cannot be a boundary. What you got to do is you got to close them, right? Because this is eventually going to intersect the curve and give you a closed area that's like blocked off from the rest of 3D space, and they'll tell you find the absolute maximums and the minimums. So if they don't give you a square or a triangle, then they have to give you either an ellipse or a circle. So my general rule of thumb is if they give you a bunch of straight lines, use the approach we just went over earlier. where you go through every single line that they give you on this boundary, draw it out, plug it in, do your derivatives, and you're done. If they give you a curved thing, you're going to do what we're going to do soon, which is parameterize it. I think I was taught, in my class at least, I think I was taught to isolate your variables and basically draw the region out like we did previously, except with these kinds of surfaces. But I really don't like doing that, and I think parameterizing it is way easier. Okay, but first step, of course, is find your critical point and see if it lies in your, what do you call it? In your region. So if we take the derivative, you get 2 in the x direction, so partial z partial x equals 0 equals 2x minus 6. So then x equals 3. And then partial z partial y equals 0 equals 2y. Yeah, so then y equals 0. So this is our critical point. Now, does that lie in our boundary? Let's see. So if we plug it in, you're going to get 3 times 3 squared plus 9 times 0 squared equals, well, really this is an inequality because we want it to be inside. So it doesn't have to equal 1. It just has to be less than or equal to 1. Okay? And then if you simplify this, you're going to get 27 is less than or equal to 1, which is obviously not true. So our critical point actually doesn't lie on inside of this boundary, so we can't consider it. Now, what do we do? Well, we could see where this, okay, well, first we'll have to parameterize it. So parameterizing an ellipse is very, hold on, wait, I'll be right back. I'm going to turn on the lights because it's going to be a bit dark. Okay. Parameterizing an ellipse is really similar to parameterizing a circle, where you use sines and cosines. So sometimes I forget how to exactly do it, but I guess let me just work through it. So for this ellipse exactly, I guess the way I remember it is I'll draw out, or I'll write out a equation like this. This is a circle because you could factor out the 2. So that means this guy's a radius of 1. Okay. So, okay, yeah. And you could parameterize this guy as just cosine t comma sine t. Okay, so this guy, you can parameterize him like this. You could say, wait just a moment. Okay, this is how you parameterize him. You say 1 over 3 cosine t, comma 1 over 9 sine t. Okay? This is the parameterization of this boundary, this ellipse, in 2D, right? In x and y. Now, oh yeah, and notice he doesn't have a z element. What that means is the z element is free. Z can be anything. So let's just write it out just so you could see, and let me x out all of the previous things. So minus 6. Oh, and let me write out our new equation. So minus 6x plus 9. Okay, so that's our new paraboloid. Okay, and then our new ellipse is this. 1 over 9. 1 over 9 sine t. Okay, and then from 0 to 2 pi. Yeah, look at that. Okay. So there's our little ellipse. And as you can see, he is obviously not hitting that critical point that we have for a parabola. But if you were to, here, let me write his normal equation actually, just so, because 3x squared plus 9y squared equals 1. Oh wait, did I do something wrong? Okay, yeah. Wait, apologies, I made a little bit of a mistake. This is 1 over root 3, then 1 over root 9, so this is 1 over 3. Okay. And yeah, that's because you could do this, and then that's going to be root 3 squared. This is root 9 squared, and you could move them around and you get these results. Okay. So, okay, yeah, and then if we extend this guy to 3D, you could see this. So that red thing is our parametrization. The blue is the extension along the z-axis. And see how he intersects our surface in this kind of ellipse, right? It's like that. Maybe it's easier if we see it from this way. But yeah, there's like kind of an ellipse. And now we can parameterize that intersection, and that's really important. Okay, so let's parameterize that intersection. So how do we're basically just finding their intersection. So we're basically going to be giving this guy a z component, and we're going to be finding what that z component is. So we plug these values into this. So we're going to have 1 over root 3 cosine t squared. I'm literally just plugging this x into this x. And then plus 1 over 3 sine t squared. And then minus 6 times 1 over root 3 cosine t plus 9. And this is all equal to our z. Okay? So we can take this entire equation and plug them back in here. And that's our z. Now another thing to note is that this z value, that's how we measure height. Because when we say a minimum or a maximum in 3D space, we're just asking for the value of how high along the z-axis is a point. So this z function gives us the height of that parametrization. Okay, so we could simplify this just a little bit. Have 1 over 3 cosine squared t plus 1 over 9 sine squared t minus 6 over root 3 cosine t plus 9 equals z. Now let's add this parameter. So 1 over 3 cosine squared t plus 1 over 9 sine squared t minus 6 over root 3 cosine t plus 9. Okay, why is it red? Okay, there we go. Yeah. So this is the entire parametrization we just found. There's our z component, pretty long. And it's that green ring around the, see how it's kind of an elliptical shape? So yeah, So what we can use this for is because that z function gave this, remember, before when we just had x and y, it was down here, like this, but now we gave it height. And the part of that parametrization that gave the function height was the z component we just found. So all we need to do to find our min and max in this region is find boop that point and boop this point. Okay, and those are our min and maxes. Remember, because the critical point isn't even in the region. Okay, so how are we going to do that? Well, you can treat it similarly to how we did with when we said f of x earlier. This is a function of t. This is f of t. And how do you find the mins and the maxes of a function? You take the derivative. So we're doing the same thing. You have 2 over 3 cosine t times derivative of cosine is negative sine t. And then this is going to become 2 over 9 sine t times cosine t. And then you have minus 6 over root 3. Oh, take the derivative, that's going to be negative sine. Okay. And then we're going to set this equal to 0, which is, it's also nice that we can simplify this. So if we simplify this, 3, that's going to be minus 6 over 9 plus 4, that's going to be minus 4/9 cosine t sine t plus 6 over root 3 sine t equals 0. All right, so there's 2 ways we can make this guy 0. At t equals 0, right, because sine of 0 is 0, so if we have sine in both terms, that's going to give us a 0. Also, you can cancel out this sine term, right, factor, divide by both sides, and that's going to give us a value of t that is not equal to 0. And then, so now we're going to have minus 4 over 9 cosine t plus 6 over root 3 equals 0. And now we can move these to both sides. So you're going to have minus 6 over root 3 equals minus 4 over 9 cosine t. Isolate, you could start by isolating t. You're going to get 9 times negative 6, that's negative 54. Oh, you could cancel out the negatives as well. You're going to get 54 over 4 root 3 equals cosine t. And then take arc cosine. And you could simplify this, you could get 27 over 2 root 3. So these are 2 t values. One's going to give us a max, and one is going to give us a min. Yeah, we could also even just plug them back in here and see what those values are. Yeah, if we plug in t equals 0, this is going to go to 0. This is going to be 1 over 3 minus 6 over root 3 plus 9, which is, let's see, 1 over 3 minus 6 over root 3 plus 9. So this is about 5.87. Now if we plug this ugly number in there, you have arc cosine of 27 over 2 root 3 Wait, is that even doable? Well, I think I made a silly. There should be a t-value for that. I mean, I see what the issue is that that's out of the range for cosine. But anyhow, let's check. At t equals 0, you're gonna have what point? This was our parametrization. You're gonna have 1 over root 3, comma 0, comma about 5.87. Yeah, and that's our minimum point right there. Now our max point, we likely made some kind of error. Let's see. Yeah, so we had that. We use the same derivative for both. If we move to another side, maybe we'd have to play around differently with it. Hold on. Okay, yeah, so here I just noticed we can't cancel out these signs, because if we do, then we get this number which is undefined. So the only way we can get this expression to equal 0 is by ensuring that the signs are 0 as well. So not only can t be equal to 0, but it can also be equal to pi. Or 2 pi, but 2 pi is at the same place as 0. Okay, so if we plug in pi, you get, let's see, what do you get? You're going to get 1 over 3 plus 0 plus 6 over root 3 plus 9, which is about 12.79. We'll say 12.8. 12.8. Yeah. Okay. And there are 2 min and maxes, so one's down there, one's up there. Okay. So yeah, curvy things, parameterize it. It's way easier that way.